Hello. This video includes information on the introduction to equilibrium and equilibrium expressions.
Chapter 13 starts looking at equilibrium, and we're actually going to be using that for a good part of the rest of the semester. So it's super important that you get a good foundation over the next couple of classes because it's going to carry you through a good part of the rest of the semester. So when we talk about equilibrium, okay, when we look at a reaction, it takes place in such a way that the concentration of the reactants decreases as time progresses. And it's going to continue to do that until we get to a point where the conversion of the reactants to the products is no longer favored. So to kind of go back a little bit to the free energy stuff we talked about in thermodynamics, when we look at a reaction initially, right at the beginning, the free energy of the forward reaction is negative, which means the forward reaction is spontaneous. But the reverse reaction or the backwards reaction has a free energy value that's positive, so it's non-spontaneous. But as the reaction progresses, the negative values are going to become closer and closer to zero, and the positive values are going to become closer and closer to zero until eventually we get to a free energy value of exactly zero. And then we say that the reaction is at equilibrium. And when we talk about equilibrium, the concentration of the reactants become a constant, and the concentration of the products become a constant. Now, they don't become equal to each other, but they stop changing. And when we get to that point, we say that we've reached equilibrium. So if we wanted a graphical representation of that, if we were to start right at the beginning of the reaction, all we have are reactants. And as the reaction progresses, the amount of reactant goes down and the amount of product goes up until eventually the amount of product becomes a constant and the amount of reactant becomes a constant, and we reach this equilibrium in our reaction. Now, when we talk about equilibrium, depending on the way we look at it, we could say that it's static or it's dynamic. Now, if we were to look at it at the macroscopic scale, meaning if we were to just look at a container that has a reaction that's at equilibrium, it would look like nothing's happening. It would be static. The concentration of the reactants are a constant. The concentration of the products are a constant. They're not necessarily equal to each other, but they're not changing, so we wouldn't see anything with the naked eye. So if we were to look at, let's say, nitrogen gas reacting with hydrogen gas to produce ammonia, at the beginning, okay, the amount of nitrogen and hydrogen is going to go down as the reaction is produced. The amount of ammonia is going to go up until we reach equilibrium, where the concentration of hydrogen will be a constant and the concentration of nitrogen will be a constant and the concentration of ammonia will be a constant. Now, this is a graph of concentrations. Since the concentrations aren't changing at the macroscopic scale, we would say that it's static. But if we were to look at the microscopic scale, if we were to go all the way down to the molecular level, equilibrium is actually very dynamic. The forward reaction is taking place and the reverse reaction is taking place. But they're taking place at the same rate. So the net change is zero. But here's our rates, a little bit of a different graph, okay? At the beginning, the rate of the forward reaction goes down because we're consuming reactant. The rate of the reverse reaction is going up because we're producing product. And when the rate of the forward reaction equals the rate of the reverse reaction, we're at equilibrium. But that doesn't mean the reaction stops. It's still going in the forward direction. It's still going in the reverse direction. It's just that their rates are equal, so the concentrations don't change anymore. So essentially that means that when we have a reversible reaction at equilibrium, we don't run out of anything. So let's say that we have phosphorus trichloride and we react it with chlorine, and we're going to produce phosphorus pentachloride. Now the arrow's going in one direction. That's essentially saying that this reaction is going to go to completion. It's going to continue until one of the reactants, the limiting reactant, runs out. Now, kind of a way to bookkeep this a little bit, okay? We make what's called an ICE chart. Okay, we've got our initial amounts, we've got the changes that take place, and then we've got the ending amounts, ICE, an ICE chart. So we've got the phosphorus trichloride here, and the chlorine here, and the phosphorus pentachloride here. Let's say that we start the reaction, and initially we don't have, or we have 1 mole of PCl3, and we have 2 moles of Cl2, and since it's at the very beginning, we don't have any product yet. Okay, well, the stoichiometry tells us it's a 1 to 1 to 1 ratio. So X amount of PCl3 will react. X amount of Cl2 will react. It's a 1 to 1 ratio. And X amount of PCl5 will be produced. Okay, well, if the reaction goes to completion, all of our limiting reactant is going to react. So if we have 1 mole and 1 mole of it reacts, there isn't anything left. This says LR for limiting reactant. So if we have 2 moles here of chlorine and only 1 mole reacts before we run out of PCl3, we're going to have 1 mole of Cl2 at the end, and it's our excess reactant, what's left over. And we had no PCl5, but 1 mole is produced, we end up with 1 mole as our theoretical yield. And again, it's a 1 to 1 to 1 ratio because of the balanced equation. But this reaction is actually a reversible reaction. We don't end up consuming anything. So we're going to look at just a slightly different ICE chart. And we call them ICE charts: initial, change, end is the way we're going to call that. So let's say we start out with 1 mole of PCl3 and 2 moles of Cl2, and we don't have any product to begin with. Again, it's a 1 to 1 to 1 ratio that they react in. But because it's a reversible reaction, we don't ever end up running out of anything. Some of this reacts, but not all of it. So something less than 1 mole of this reacts, something less than 1 mole of this reacts, and something less than 1 mole of this is produced. And what we end up with is 1 minus X, whatever that X might be, we'll define later. That's how much PCl3 we'll have at the end. We'll have 2 minus X for our chlorine at the end. And we'll have X of our PCl5 at the end. They're all reacting where X amount is being consumed and produced, but this time, because it's not reaching or it's not going to completion, less than 1 of everything is being produced and consumed. When we talk about equilibrium reactions, they always result in a smaller amount of product than we predicted by the theoretical yield because it doesn't go to completion. A reaction is said to be product favored if at equilibrium we have a higher concentration of product than we had reactant. We say that the reaction is reactant favored if it doesn't proceed very much before reaching equilibrium. So we end up with a lot more reactant at equilibrium than product at equilibrium. Can we change whether the reactants or the products are favored? We can. It's actually called Le Chatelier's principle. And that's something we're going to talk about. So let's look at an example. Okay, let's say that we have N2O4 in a container. Okay, it will spontaneously start to produce NO2. But as NO2 is produced, it will start to reproduce N2O4, and eventually we'll get to equilibrium. Kind of a cool thing about this particular reaction is that N2O4 is a clear, colorless gas. And NO2 is kind of a brownish colored gas. So at the very beginning, because all we have in the container is N2O4, it's a colorless gas. Now, when the reaction starts to go, we're going to start to produce NO2. And the reaction vessel starts to turn a little bit kind of yellowish brown. And eventually it becomes a constant color of brown. And this is the equilibrium ratio of reactants to products. Now, the reactants are still producing products. The products are still producing reactants, but the concentration of reactant and the concentration of product will be a constant at equilibrium. So is the reaction above product favored or reactant favored? Well, what we do is we look at what we have at equilibrium. We count up how many molecules we have. Well, we have a lot more NO2 molecules at equilibrium. Then we have N2O4 molecules at equilibrium, which means that the reaction is product favored. The reaction proceeds to produce a lot of product before the rate of the forward reaction equals the rate of the reverse reaction in our systems at equilibrium. We're going to look at what's called an equilibrium constant. So let's say that we have A reacting to produce B, but it's a reversible reaction. So B, once it's produced, will start to reproduce A until we get to equilibrium. Well, the rate of the forward reaction will equal the rate of the reverse reaction. So we can just take those two equations, set them equal to each other, and then because K's are constants, we can isolate the K's. So K for the forward reaction over K for the reverse reaction, okay, this is just a constant, equals the concentration of B over the concentration of A. And what that's going to lead us to is what we call an equilibrium constant. Again, we've got our forward reaction rate slowing down. We have our reverse reaction rate speeding up until the rates are equal and equilibrium is achieved. Again, that's not the same thing as saying the concentrations are equal when we're at equilibrium, but the rates are. And that's why we kind of jumped up and did some stuff on rates before we went back and talked about equilibrium. So how do we come up with equilibrium constants? All right, here's an equation. We have A reacting with B to produce C and D. Okay, so those are the reactants and the products. This is what we call our equilibrium expression. We use a capital K here. We may or may not see this EQ, okay, which stands for equilibrium. It might even have a C here because we're talking about concentrations, or it might not have anything there at all. The brackets mean concentrations, molarities. The superscripts, the exponents, are the coefficients in the balanced equation. So when we write an equilibrium expression, it's the concentration of the products over the concentration of the reactants raised to the power of the coefficient in the balanced equation. And that's called an equilibrium expression. K is a constant, okay? And it doesn't have any units to go along with it. And another important thing is when we write an equilibrium expression, solids are not included and solvents are not included. Liquids are not included. Gases can be included. Ions in solution can be included because we can talk about them in terms of concentrations, but solids and liquids would not be included in an equilibrium expression. Now, some things about K. Okay, K is a constant. Okay, the only thing that will change K for a particular reaction is temperature. And when we talk about a given temperature, there's only one K because it's a constant. But there are many different combinations of reactants and products that can give us that value. So the equilibrium positions can vary. When we talk about homogeneous equilibria, and equilibria is just plural for equilibrium. Homo means the same, so all the things in that equilibrium are in the same state. So as an example, if we have aqueous HCl at equilibrium with hydrogen ions in solution and cyanide ions in solution, this is a homogeneous equilibrium. They're all aqueous. And we can write a K expression. This just says C because they're in terms of concentrations. It could say EQ, sometimes it doesn't say anything. It's the product over the reactants raised to the power of the coefficient in the balanced equation, and these are all ones. So there's a one assumed to be here, here, and here. This is also a homogeneous equilibrium because they're all gases. Now, when we talk about gases, we can talk about gases with respect to their molarities, their concentrations, or we could talk about them with respect to their pressures, and they're directly related to each other. So we could say it's the products over the reactants raised to the power of the coefficient in the balanced equation in terms of concentrations. That's what the C is for. Or we could write it in terms of their partial pressures. Now notice it's still products over reactants, and they're raised to the power of the coefficient in the balanced equation. The only difference is these are partial pressures and these are concentrations. And how are they related? Well, the equilibrium constant in terms of partial pressures will equal the equilibrium constant in terms of concentrations times RT raised to the delta N. Okay, what does delta N mean? Well, delta N means the difference in the coefficients in the balanced equation. So in this case, 2 minus 4. Okay, and R is going to be 0.0821, and T is going to be in Kelvin. So if we know Kc, the equilibrium constant in terms of concentrations, we can figure out K, the equilibrium constant in terms of partial pressures. This equation allows us to relate the two. Here we have three different heterogeneous equilibria. Okay, that means that not everything in the reaction is in the same phase. So in this case, we've got a solid here, we've got a solid here, and we've got a gas here. So it's a heterogeneous equilibrium. And we want to write the equilibrium expression. Well, it's products over reactants raised to the power of the coefficient in the balanced equation, except we don't include solids and liquids. So for this first reaction, our equilibrium expression would be the concentration of oxygen raised to the third power. We're not going to include KCl, and we're not going to include KClO3 because they're solids. The second reaction is a heterogeneous equilibrium. We've got two gases and a liquid. We're going to write the K expression by taking the products over the reactants raised to the power of the coefficient in the balanced equation, but we don't include liquids. Well, this time our product is a liquid. Well, we can't put that into our equilibrium expression, so we would just put 1 in the numerator. And then we have our reactants in the denominator. So our K expression for this heterogeneous equilibrium would be 1 over the concentration of hydrogen squared times the concentration of oxygen to the 1. Again, it's the concentration of products over the concentration of reactants raised to the power of the coefficient in the balanced equation, excluding solids and liquids. So we've got our third heterogeneous equilibrium, and we want to write our equilibrium expression. So we've got our products here. Okay, they're aqueous, so we're going to include those. Aqueous doesn't mean liquid. It means ions in solution that we can talk about in terms of concentrations. And then we've got our reactant here, but it's a solid, so we're not going to include it. So our K expression would be the concentration of manganese ions raised to the first power, because there's a 1 here, times the concentration of carbonate raised to the first power, because there's a 1 here, over 1, because this is a solid. Now, once we can write an equilibrium expression, and it's always the first step in these kinds of problems, we're going to kind of be working the problem one of two ways. Either we're going to be given the concentrations and we can calculate K, or we're going to be given K and we can calculate the concentrations. But the starting point for every equilibrium problem is writing an equilibrium expression.